The question that I usually get at this point is how do I know the shape of x squared minus y squared? The shape is you have to memorize it. You have to sit down and memorize the atomic orbitals for the s, p, and d atomic orbitals. Remember that I'll never ask you to draw an f orbital because they are incredibly complicated, and not even graduate students are asked in drawing an f orbital. That's usually left to computational work. So let's start by writing down our principal quantum number. Remember that the principal quantum number gives us the energy and size of the atomic orbital. And we're going to also fill in the L value for this atomic orbital, which is going to give us the identity. What set does this atomic orbital come from? Is it an S, P, or D atomic orbital? So the N value is the number that's right in front of the letter D. It's the number that begins in our atomic orbital, and that's going to be equal to 4. And our L value, since we're talking about a d orbital, a d orbital has an L value of 2. And in addition to telling us the shape or the type of orbital that we're supposed to draw, L also gives us information of the number of angular nodes our atomic orbital has. Remember that an s orbital has no angular nodes, a p orbital has 1 angular node, and a d orbital has 2 angular nodes. So we should expect our drawing to have 2 angular nodes for this 4d x squared minus y squared orbital. But we also have to worry about the number of radial nodes. Now I'm going to continue using the same color motif that we did for the previous 2 examples. So if we have any angular nodes, which we should have 2 here because L is equal to 2, I'm going to use the color yellow for the line that represents it. And then if we have any radial nodes for this atomic orbital, then we will represent that node with the color green. In terms of the shading for the phase of the atomic orbital, I'm going to continue the same motif that we had for the last example, where I'm going to use the color like red, orange, and like light blue. So I haven't changed the color set at all since I started since I had our lecture on Wednesday actually. So it should remain the same. Now I'm gonna plop over to my recording software to make sure that I am recording. This really reminds me of COVID now. Ah, sweet. I am still recording. We're in good shape. For those who do not know, I like to use OBS. In fact, none of y'all know. I like to use OBS to record my lecture videos when I used to teach completely online during COVID times. So let's assign our L value, the number of angular nodes here. So since L is equal to 2, I should have 2 angular nodes. And in order to find the number of radial nodes, recall that the equation is n minus L minus 1. Since our n value is equal to 4, our L value is equal to 2 minus 1. 4 minus 2 is equal to 2. 2 minus 1 is equal to 1. So we're going to have 2 angular nodes and 1 radial node. I have forgotten a tangent here. My Surface does not necessarily like OBS, and as I'm writing on this screen, I can feel all the heat coming off of it because it's working overtime trying to record the lecture without melting under the strain here. I remember if I had a really long like review video and I wouldn't stop the review video, this is something I used to do at UC Davis when I taught there. The Surface would be like hot to the touch. I'm surprised that it's still functioning today. Okay, so we know that we have 2 angular nodes and we have 1 radial node. So let's start by drawing our Cartesian coordinate system. And remember, we're only drawing these atomic orbitals in 2 dimensions. I don't want to draw them in 3 dimensions because then I have to worry about the right-hand rule. And some of y'all haven't even taken physics, which means you don't even know what the right-hand rule is. So we're going to draw our atomic orbital as a 2-dimensional representation. Again, it's as if I'm taking a jawbreaker and I'm slicing it in half and I'm looking at the cutaway of the jawbreaker. So in white, I'm going to draw my Cartesian coordinate system. Up, vertical line, and a horizontal line. And since this is a 4d x squared minus y squared atomic orbital, I know that the entire orbital is along the xy plane. So I'm going to draw the vertical axes as being y and the horizontal axes as being x. Here, it's not going to be x or z. It's going to be x because I know that the atomic orbital is in plane in the xy plane. And this is going to be true also for the other d orbitals. They're all aligned a specific plane in the 3D Cartesian coordinate system. So a dxy is an atomic orbital that's along the xy plane. A dxz is along the xz plane. So that's an easy way for you to determine whether I'm how to assign my axes here. All right, so what I want to do next is, before I draw anything, I want to draw my radial node in green, and I have two angular nodes. Now, again, the question that usually comes up at this point is, how do I know where to draw my angular nodes? Again, you have to memorize what the orbitals look like. That will tell you where the angular nodes are supposed to go. And for just an x squared minus y squared d orbital, the lobes in which the electrons can exist are going to be parallel, aligned with the xy axes. So my angular nodes are actually going to be off. They're going to be 45 degrees off of the xy axes. So I'm going to draw the first one from the origin out in this direction. This is my first angular node. And then I'm going to draw the second one to make kind of like this X here. Now, on a test, if I ask you to draw an atomic orbital, I'm going to ask you to not only label your axes, but you also have to label the nodes, whether it's an angular or radial node, and then you also have to show your phase. Your phase, again, can be done with a plus or a minus. If you do have color pencils on you when you're taking the test, you could use color pencils, but I'm not expecting you to. So you could always use filled in or not filled in to represent the phase as well. So I'm going to label, and it doesn't matter which of these angular nodes I label, one or two. I'm just going to label them so that if I were grading this question, I know that the student can identify what the angular node is. So I'm going to label this one angular node number 1. And then this one's going to be angular node number 2. Our radial node is going to be a circle. It's technically a sphere in three-dimensional space, but again, we're not drawing these atomic orbitals in 3D space. That's too artistic for us, right? It's too much. Some of y'all, I'm sure, could do it. I certainly cannot. So I'm going to do a 2D representation, which is just a circle. And I'm going to also put a little arrow to say that this is my radial node. So that if I were grading this question on a test, I could obviously tell that the student has the ability to distinguish what's an angular node and what's a radial node. The nodes are, again, the representation of where the electron will never be found. Remember, we're treating our atomic orbitals like waves. They're called wave functions. And the electron, whether it's an upspin electron or downspin electron, can exist in certain portions of this atomic orbital, but you will never find it, ever, inside of a node. It will always exist in the respective phase that it has been assigned to. So now I'm going to change colors here so I can draw my atomic orbital. I'm going to start with the light blue. Again, where I begin my phase and begin my drawing doesn't matter. The only thing that matters, the rule that I have to obey here, is whenever I draw my first lobe, if I draw a lobe in which I cross a node of any kind, I have to switch colors. I have to switch phase. So I'm going to start by first drawing my lobe. This is going to look kind of like a 4-leaf clover in the center like so. Okay. And the way I'm going to draw this 4D x squared minus y squared orbital is I'm going to start with this lobe and I'm going to work clockwise. And I'm going to go outside and I'm going to work clockwise outside. And when I finish my diagram, I'm going to go back to the drawing and make sure that all the phases make sense here. So that when I cross from one lobe to another lobe, the phase changes its color. I go from blue to red. I go from plus to minus. I go from a filled-in lobe to a non-filled-in lobe. whatever we're going to do to represent the phase. So going clockwise, oh, that's not what I wanted to do. I erased my circle. Here we go. Going clockwise from here to here, I cross this angular node. Since I only cross one node, the color is going to go from blue to red-orange. So I'm going to draw another lobe in this direction, like that. I'm going to fill it in. And I'm going to continue going around in the clockwise direction. So from here, I know that's a little bit hard to see my laser pointer because they actually have like the same color. I'm going to go from here to here. I'm going to go from dark red-orange to blue again. So I'm going to change the color again to blue. Go around. Fill that in. And then I'm going to fill in the last one going from here to here back to red. All right. We're looking pretty good so far. There is a radial node. Since there's a radial node, I better have a lobe on the opposite end of this node. If there wasn't a lobe over here, there's no reason for me to draw on this radial node. So because I know for a fact based on the math that there is one radial node, I know that I'm going to have to draw some lobes on the outside of this green circle. So going from here, this red lobe, to here, I cross the radial node, which means the color should go back to blue. And as I stated in class, as you get further and further away from the origin of my Cartesian coordinate system, the lobes increase in size. It's almost as if like they become more and more diffuse. So going from this red blob to here, I'm going to go to blue. And I'm going to try and kind of continue the same shape that I have for this four-leaf clover. I'm probably going to have to... Oh, I think it'll be fine. When I draw this lobe, it's probably going to get in the way of this green arrow, but it should be okay. If we have to erase it and move it out of the way, we can do that. Okay, so let's go from this blue lobe to down here. That's going to be red because I'm crossing an angular node. I'm going to, again, draw this big old lobe like that. Fill it in. I'm going to go from this red lobe back over here that crosses this angular node. So this is going to be blue again. Oh yeah, we're cooking now. And then finally, we're going to go back to the top of this diagram for red. And yeah, let's move this out of the way. Let's redraw this somewhere else so that we have space. Let me pull out the green marker again. Let's put a little arrow here and say radial node. On a test, I'm not going to lie to you, it would be pretty rare for me to ask you to draw a d orbital that has a principal quantum number n greater than 4. Because if I had a 5d orbital, then I'm going to have 2 radial nodes. And that's going to be a pretty complex atomic orbital for you to draw on a test. So I would say 98% of the time you're going to get, if you do get a d orbital, it's going to have an n value of either 3 or 4. I would have to be exceptionally angry for whatever reason to give you a 5d orbital of some kind. Now, something to note about this atomic orbital is when I go from any of these center, let's just pick this blue one so that you can see the laser pointer. If I choose any of these center lobes and I cross the origin, you'll notice that I cross both of these angular nodes. So some of you might be thinking, hold on a second, Dr. O. If I go from here to here, I just crossed an angular node. The color should be opposite. The truth is, though, I crossed 2 angular nodes. So because I crossed 2, there is no color change. It's as if when I go from here to here, you cross the first angular node, it goes to red, and then you cross the second angular node, and you go right back to blue. So we're not breaking any rules in this diagram by going from here to here. It's still obeying the rule that if you cross an angular node or a radial node, the phase has to change. So this is the last example for section 6 for electrons. Now, what we're going to spend the remainder of this lecture, I should have brought coffee or water with me because feels like I'm coughing up a storm. What we're going to do in this next section is we're going to fill these atomic orbitals with electrons, because each atomic orbital can hold up to 2 electrons, one that's going to be spin up, one that's going to be spin down. So as an example, if I were to put 2 electrons in this 4d x squared minus y squared atomic orbital, the spin up electron is going to reside, you will find it potentially, because remember, these are probability maps. You can't pin down exactly where the electron's going to be. We only have a probable location of where it's going to be. For an upspin electron that we've assigned to these blue phase lobes, it's either going to be in this blue phase, or in this blue phase, in this blue phase, or in that blue phase. And that upspin electron is essentially teleporting to any of these locations where the phase is blue. The downspin electron, if I were to put that second electron inside of this atomic orbital, will be found wherever the red lobes are. So that's also going to be kind of popping in and out of reality in any of the red lobes that you see on the screen. Now, what would be very difficult and tedious to do is to, as we fill in electrons into our atoms, having to draw all the atomic orbitals and filling in all the electrons for all the atomic orbitals for any given atom. That would take forever. If I were to literally sit down and draw all the atomic orbitals for, let's say, iron, and I were to fill in all the appropriate electrons that iron has, I'm going to be sitting down for a week drawing different atomic orbitals until I filled in all my electrons. That's going to take forever. So chemists and physicists have come up with a notation method that we can use to quickly assign electrons to any atomic orbital that an atom may have. Because hydrogen only has a 1s atomic orbital, but if I go to iron, iron has a bunch of s orbitals, p orbitals, even d orbitals. And all of those orbitals are going to have 2 electrons in them potentially. And I need to be able to know which atomic orbitals have electrons, because not only does that give me electronic properties for the atom, meaning how many electrons the atom has, but it also tells me which electrons can make bonds, which electrons do not make bonds, which electrons are easy to remove, which electrons are not easy to remove. It gives me a bunch of information for the atom in terms of its reactivity. And that's what we're going to do in this next section. So let's move on. Periodic table. This notation, this ability to give an address for all the electrons that an atom has, is called electron configurations. And from electron configurations, we're going to learn a longhand notation and a shorthand notation. And we're pretty much almost always going to use the shorthand notation because it's just faster. And I may have made a joke that chemists like to be lazy if they can. I like to be lazy if I can. So most of the time, if you're doing anything with regards to electron configurations, it's going to be with the shorthand method. But it's still good to know the longhand method because, really because of test questions. Like that's just the truth. Because in order to understand the shorthand method, you have to understand the longhand method. We're going to talk about magnetism for a little bit, very, very briefly, which is going to continue. The topic of magnetism is actually going to continue not only for the second to the last section of the course, but it's also going to continue in Chem 401 when you learn about transition metals, because magnetism is also important in that section. And then we're going to spend the remainder of this section of notes talking about periodic trends. So if I go back to the first page here, where I have my periodic table, the periodic table, for the most part, the way we use it for stoichiometry is simply for molar masses and symbols and potentially the atomic number for a given element. But luckily, the way this periodic table is organized, it's also organized in such a way that we can determine some of the element's properties based on where it is located on the periodic table. Oh no, my desktop with my typed notes almost fell asleep. Don't fall asleep, desktop. I'm in my office at home right now, and I have like my Surface, and then I have like my desktop that I work at home with and also play games with. That's like sitting around me, so it's kind of a cluttered mess, but I'm making this work. So we're going to talk about how the elements are organized on the periodic table and how we can determine certain trends, like how can like trends like does this element behave more like a metal than a non-metal, and then we can determine whether this element is bigger than another element, such as atomic size. We can figure out how much energy is required to remove electrons. What is the likelihood that an atom wants electrons instead of removing electrons? And then we'll end it with electronegativity at the very end of this section. So the reading material, I'm going to put that up on the screen. Of course, you should all be familiar with the reading material because it's given to you in your note packet. So this is all Chapter 9 material. So let's talk about, well, first off, let me make sure that I'm still recording. Let me go back to OBS here. It says I'm still recording. I've been recording for 25 minutes. Good. Awesome. So what are electron configurations? Electron configurations, simply put, is the distribution of electrons among atomic orbitals in an atom. So what you're seeing on the screen here is like a pseudo periodic table with none of the elements filled in. But what is filled in are a bunch of principal quantum numbers. These are n values that go from 1 to infinity. And the assigned letter to the L value that we learned from the shape of the atomic orbital. So we have s orbitals, p orbitals, d orbitals, and f orbitals. And in fact, the periodic table is divided up into sections. We have the s block. These are elements that have s orbitals. D block, these are elements that have d orbitals. P block, elements that have p orbitals. And then f block, elements that have f orbitals. Now, in an effort to make sure I don't confuse you here, if I were to choose an element over here, let's say it's in the 3p section of the periodic table, it doesn't mean that this element only has 3p orbitals. In fact, what it has is all of the previous orbitals as well. So if I were to talk about, let's say I'm looking at my periodic table on my wall here, phosphorus is down here. Phosphorus has 3p orbitals, but it also has 3s orbitals, 2p orbitals, 2s orbitals, and a 1s orbital. So all of those orbitals, all the way up to the location of where phosphorus is on the periodic table, all those orbitals are going to have electrons in them. Some of them are going to not be completely full, but a lot of them are going to be completely filled up with electrons. If I was looking at a much heavier element, let's say I'm looking at something that's in the 5p area, then it's going to have some electrons in the 5p orbital, a bunch of electrons in the 4d, the 5s, 4p, 3d, all the way down until we get back down to 1s. If I was trying to write down the configuration for something in the f block, then I have to go from the f all the way back to the p and the d. I just have to keep going back until I get to the 1s. And that would be all the electrons that an element that is located down here would have. So let me pull my notes down here a little bit. So what we're going to do here is we need to recall how many atomic orbitals there are for any given set. So there's only one s orbital, right? There's 3p orbitals. There's a p sub x, p sub y, p sub z. So on the next page, we have some notes here to kind of reflect that, to remind you that any given L value has some number of m sub L's. Remember that if your L value is 1, the acceptable m sub L value is -1, 0, and 1. Well, that means that I have 3 different p orbitals, because L being equal to 1 means I'm talking about a p orbital. And those 3 p orbitals are going to be the p sub x, p sub y, and p sub z. Each of these atomic orbitals, each individual atomic orbital can hold 2 electrons. The entire set, since there's 3 of them, and I can hold 2 in each, is going to be 6 electrons. If I'm talking about d orbitals, there's 5 d orbitals. dxy, dxz, dyz, the dx squared minus y squared that we drew earlier, and then the black sheep, the dz squared, that looks like a dumbbell with a donut around it. Since I have 5 of these, and each can hold 2 electrons, well, I have a total of 10 electrons that I can put in these atomic orbitals. And in fact, what's really convenient about this setup and how we've assigned our atomic orbitals, remember that it's not necessarily that it's convenient for us, it's just this is how the math worked out when we derived the shapes for the atomic orbitals. If I go to my periodic table real quick, let's say that I'm looking at this row right here of elements that are in a D block section. There's 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this corresponds, If I were looking at zinc here, zinc can have a total of 10 electrons inside of its atomic orbitals, because there's 5 atomic orbitals, each of them holds 2. That works out to 10. If I was looking at neon, neon's part of the d orbital, oh, not sorry, the p orbital set. And since there's 3 p orbitals, then I should be able to put up to 6 electrons in this set here. Well, 1, 2, 3, 4, 5, 6. So that makes sense here. So let's go back to our notes here. So there's 2 electrons maximum that can be put into s orbitals, 6 that can be put into p orbitals, 10 that can be put into d orbitals, and then 14 that can be put into our f orbitals. Now there's a problem that we need to account for. There is an order in which I fill in my electrons into atoms. So if I go back to my little pseudo periodic table here, let's say I wanted to look at the electron configuration for an element that's located in the 3p block. Again, let's use phosphorus as the example since we used it previously. All right. If I want to fill that phosphorus atom with electrons, I can't just willy-nilly fill in the electrons in the 3p orbitals first. That's wrong. The way we would actually be filling them in is from a low energy orbital all the way up until we get to where phosphorus is located on the periodic table. And there's a rule that explains why these electrons fill in from low energy orbitals to high energy orbitals. And we know that the 3p orbital is higher in energy than 2p because the principal quantum number, 3, is greater than 2. And we learned from the previous section that as n goes up, the energy goes up. And electrons have a really bad tendency, in fact I would say it's a good tendency, it's not even a tendency, they just do this. Electrons always locate the lowest energy place that they can exist in. All right. So if I have a stray electron, a free electron in space, and I let that electron go, that electron is going to do everything in its power to try and find the lowest energy availability that it can so that it can be low energy. Because things in the universe like to be in a low energy state. They like to be chill. They don't like to be all riled up. Now the rule that explains this to us is called the Aufbau principle. So the Aufbau principle, also known as the building up rule, is that electrons always fill from lower quantum numbers to higher quantum numbers. You will never fill an electron from a higher orbital down to the low orbital, right? You always start from the low and then you go to high. So it's as if a nice analogy that I've used in previous classes. It's almost like you've walked into a big auditorium and you're gonna watch like a jazz band or something, and you walk in from the bottom of the auditorium, and because you really want to see the jazz band up close and personal, you're gonna fill in by sitting down on the seats that are closest to the jazz band. That's going to be the low energy seats because you didn't have to walk upstairs or anything. You just sat down. Well, as those seats become unavailable, as people pour in, they have no choice but to go up to the next row, and then the next row, and then the next row until everybody's inside of the auditorium to watch the jazz band. So that's our Aufbau rule. The second rule that we have to obey is called Hund's rule. Hund's rule is a little bit more detailed into how we fill our electrons into these atomic orbitals. It says you fill degenerate. Now, when you see the word degenerate is a very fancy word for same energy. That's all degenerate means. You fill degenerate same energy orbitals singly first. Filling electrons singly is lower in energy than pairing electrons due to electron-electron repulsion. So here's what I'm going to do here. I'm going to draw 2p orbital sets. And I'm not going to draw the actual atomic orbital. We're going to represent the 2p orbitals, or these 2p orbital sets, as a series of squares. So we can say that this is like, in fact, I'm not even going to use the number 2, I'm sorry. We can say this is the p sub x, this is the p sub y, and this is the p sub z. And I'm going to draw another set. My surface is getting really hot. It's not liking this. You could do it, surface. You have to hold off for another 45 minutes. So let's say P sub X, P sub Y, P sub Z. I'm going to pretend that I have 3 electrons, and I have 2 pairs of 3 electrons, or I have 2 different sets of 3 electrons. And I'm going to fill in the electrons into their seats, meaning these 3 p orbitals, the P sub X, P sub Y, and P sub Z. And I'm going to fill them in 2 different ways. The first way, because I know every single atomic orbital can hold 2 electrons, I know one is going to be upspin and one is going to be downspin. So there's my first 2, and then I'm going to fill in my last one like this. That's one way I can fill in these electrons in atomic orbitals. The second way is to spread them out like this, in which there is an upspin electron in every single every single available spot that it can go to. All right. So electrons are negatively charged. And if I take 2 electrons and I try to put them in the same space as each other, they're going to try and repel each other. And the closer and closer you try and get these electrons to be, close to each other, they're actually going to be, you're forcing them in a higher energy state because you're pushing them closer together where they do not want to be close together. And they're going to try and repel each other. And if I have these 2 different sets that I have to choose from to fill my electrons and atomic orbitals, this is going to actually be a higher electron set because these 2 electrons are paired up. And what I could have done is by spreading them out evenly would give me a lower energy set. So I'm going to write in red orange, this is higher in energy, and this is going to be lower in energy because I've spread out those electrons evenly in one spin direction. Now, a question that you might ask is, Dr. O, what if I want to fill in one more electron into this atomic orbital set? I want to put in a 4th electron. Let's say that the element that I'm looking at has an electron configuration where it needs one more electron so that I can write down my electron configuration. That 4th one has no other choice but to fill in into, well, it doesn't really matter which position it goes into, but it has no other choice, but it has to fill into one of these atomic orbitals. And the reason I'm gonna say it fills into this position is because this is a convenience for us. In the English language, and in many languages, we read from left to right. And so the way we fill in our electrons is typically from left to right. I want to point out that the overall energy of the P sub X, P sub Y, and P sub Z atomic orbital are the same, hence degenerate. So I technically, if I were to erase this, I could have filled in my electrons 1, 2, and 3 like that, and that would still be correct because they're all the same energy. So if I'm only filling in 1 electron into this atomic orbital set, the electron has the choice of going in any of these 3. It kind of doesn't care. And at that point, it's not a question of like whether the electron's picky about which one it's going to sit in. It's more of a what's the probability that it's going to sit in this atomic orbital or this one or that one. Since there's 3 spots, it's a 33% chance that it's going to be one or the other. But let's go back to our example where I want to put a 4th electron in here. Well, if I want to put a 4th electron into this set, what I don't want to do is do that. That would be incorrect because of the final principle on this set. The final principle, the last law that we have to cover. The Pauli exclusion principle. No 2 electrons will have the same quantum number set. It is impossible to have 2 electrons to have the same exact quantum number set. So let's use an s orbital now as our example. Let's say I have a 1s orbital here, and I have another atom with another 1s orbital here, and I have 2 electrons that I'm going to put inside of these orbitals. Since I have to put 2, and there's an atomic orbital that can fit these 2 electrons, I can either fit it so that they're both in the same direction spin up, or one that's like this. Now, if I were to look at, let's say we're going to call this atomic orbital 1. And this is going to be atomic orbital 2. And on the next page, let me insert a page here. And because my surface is kind of overheating, I will not be surprised if it crashes on me every once in a while because, oh, it made it. Sweet. Awesome. Yeah, when it gets hot like this, it's like I'm playing with like fire. Literally, this thing is like really hot right now. Okay, so I have atomic orbital number 1, where I have 2 electrons that are facing the same direction, and then I have atomic orbital number 2. And what I'm going to do here is I'm going to make a little table, atomic orbital. We're going to call this electron 1. Actually, let's do this. How do I want to do this? Because I have to, yeah, let's do it like that. Atomic orbital number 1. And atomic orbital number 1 has 2 electrons. So we're going to call this electron number 1, electron number 2, and then we're going to do the same thing for the other atomic orbital, which also has 2 electrons, electron number 1 and electron number 2. And I'm going to look at all of the principal quantum numbers for that given electron, because that electron has been assigned an address, and that address has an n value, an l value, m sub l, and m sub s. So all of these electrons, regardless of whether we're talking about the ones that are inside of atomic orbital number 1 or atomic orbital number 2, have an n value of 1. Now, if you saw this and you're thinking about the Pauli exclusion principle, you're probably screaming and saying, wait, I'm already breaking the rule. Not quite, because potentially they may have different m sub s values, and we'll get to that in a little bit. If I have an atomic orbital or 2 atomic orbitals, I'm comparing their electrons from one another, and let's say that the n value is equal to 2. You can have 2 electrons have the same n value, which would be 2, but one L value from one atomic orbital might be 0, and the one for the other one might be 1. Now, in this case, all of these have the same L value. They're all 0, because I'm talking about an s orbital. And let's make sure that these are zeros by drawing a little slash through it so that you know that I'm talking about 0. The m sub l value is plus or minus L, which in this case it's still 0. So 0 all the way across. And it's when I get to m sub s that things are going to become interesting. So for the electrons in our first atomic orbital, the m sub s value for both of them are plus half. So plus 1/2, plus 1/2. Now I've broken the Pauli exclusion principle, because the address for this electron and this electron is exactly the same. I can't do that. So we're just going to write a big ol' X here and say that's wrong. You can't do that. For the second one, though, one electron is positive half, the other one is negative half, and this is allowed. So even though the address here is the same for both of the electrons, it's when we get to the spin that they're different. It's almost as if these 2 electrons reside on the same street, maybe even the same house or the same apartment complex, but one lives in one apartment and the other lives in a different apartment. So we do not have 2 electrons that are occupying the same exact space, and that would be breaking some rules. In fact, the Pauli exclusion principle is a very general way of describing why it is impossible for matter to phase into itself. So if I were to rest my hands on my table here, or if you were to press your hands up against each other, palm on palm, palm against palm, you'll notice that if you push into your palms, they don't phase through each other. You're not like a ghost, right? You just don't phase into itself. There's a force that's keeping you from pushing your hands literally on top of each other, and that force can be explained by the Pauli exclusion principle. Because if I was able to push the matter so that it's literally on top of itself, then we're about to place a bunch of electrons into the same address, and I can't do that because the Pauli exclusion principle says that my 2 electrons cannot have the same address. It's not possible. So that's a general way to explain why matter of any kind, whether it's solid, liquid, or gas, you will never see atoms literally phase into each other. It won't happen. It's not possible. But now I want to actually write down my configurations. So now that we've covered our rules, we know how to fill in our electrons from low energy to high energy. I want to actually write down the electron configurations. There are several different ways we can do this. We're going to cover, I think, 4 different diagrams, or is it 3? 3. We have first the SPDF condensed version, which is going to assign our electrons into atomic orbitals. We are going to have a shortcut method, which I'm going to show you in the SPDF version. Then we can also write down our electron configurations with orbital diagrams. Now, the orbital diagram is going to look very, very similar to this box method, where I'm representing my electrons as these up arrows or down arrows. And then finally, a little bit of a subset here would be what we call the orbital energy diagram. The orbital energy diagram is simply going to be an orbital diagram that just has an energy axis. And the reason it's important sometimes for us to see where the energy axis is because, well, these electrons can make bonds, and I can remove electrons. And we're going to see that the high energy electrons in our atomic orbital set are the ones that do things. The low energy electrons don't do jack squat. They like to chill out to the best of their ability. So I'm going to choose a random element here. Let's use yellow as our color. Let's say I want to write down the electron configuration for chlorine. I'm going to need a periodic table now. So I'm going to give you, you can pause the video, or I'm going to give you 10 seconds so that you can pull out a periodic table, because we're going to need a periodic table to assign the electron configuration for chlorine. So I'm going to look at my clock here. I'm just going to count 10 Mississippis here. We have about 32 minutes here in our hour and 20-minute lecture. Things are going pretty well. I'm trying to chill. I'm not trying to go fast here. Okay. I'm going to highlight, and let's continue using red. Where's chlorine? Chlorine's right here. Okay. So the chlorine atom is going to have a p orbital, s orbital, more p orbitals, more s orbitals, and more s orbitals. And I'm going to fill all of those atomic orbitals with electrons. And since chlorine is atomic number 17, I'm going to start all the way at the beginning where hydrogen is located. Now what I'm going to do here is I'm going to write some numbers like this. 1, 2, 3, 4, 5, 6, 7. The numbers here are the principal quantum number. So if I were to go back to the very beginning of my notes here, all I've done here is put numbers on the left so that I can assign specifically what the principal quantum number for that L letter, for the L value for that atomic number. Now you'll notice that if I'm looking at my s orbital, so I have 1, 2, 3, 4, you would think that the d orbital should start at 4, but it actually doesn't. It starts at 3. That's because the L value for d is 2. And the lowest energy value that I can assign to a d orbital that won't break the rule where the L is the same as n would be the number 3. So that's why the d orbital set starts at 3 instead of starting at 4. This is also true for the f orbitals. The f orbitals start at 4 instead of 5 or 6. So let's go back to our periodic table. So I have chlorine here. I'm going to start at the hydrogen here. And I know that if I'm talking about a neutral chlorine atom, it will have 17 protons and it will have 17 electrons. And so I have to assign all of those electrons in that atom. If I count from the beginning, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, there's 17 electrons. So starting from the very beginning, I know that the lowest energy electrons are going to be in the 1s orbital. So I'm going to say chlorine has 2 electrons in the 1s orbital. And the way I would say that is 1s2. Because I go 1s1, 1s2. And then I go down a row. 2s1, 2s2. and then I just keep going. But when I go to boron, I am no longer in the s orbital set. Now I'm in the p orbital set. So the electrons that reside in these atomic orbitals are going to be 2p. So 2p1, 2p2, 2p3, 4, 5, and 6. And the way I would write this down is not... the way I would write it down is not like this. I wouldn't go like 2p1, 2p2, 2p3. No, that's going to be forever. That is unbelievably takes forever. I would say, 1, 2, 3, 4, 5, 6. So then I have 6 electrons inside of the p orbital set that has a principal quantum number of 2. I'm going to erase this because we are going to write that down a little bit. So let's start from the beginning again. I have 1s, 2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 3s2, and when I get to my 3p set here, it's going to be 3p 1, 2, 3, 4, 5. Not 6, because chlorine only has 17 electrons. So if I go back to my page here, and again, keep your periodic table next to you so that you can see what's happening here. I said that, and I'm looking at my periodic table on my wall here. It's 1s1, 2, oh, sorry, not 1s1, 1s2, apologies. 1s2, 2s2, forgetting my letters here, 2s2, okay, very good. And then we're going to go 2p6, then 3s2, 3p5. And that is the entire electron configuration of chlorine. Now, let's say that I'm going to add an electron to this. So instead of having a chlorine atom that's neutral, let's say I have a chloride ion. What's the electron configuration for a chloride ion? Well, if I go back to my periodic table, chlorine has 17 electrons when it's neutral, but if it has one more electron, then it'll have 18 electrons. So the way I would signify that in my electron configuration, again, I have to ensure that I have 18 electrons here, not 17, because this is an ion. It has one extra electron. It's an anion. It will have the same beginning, 1s2, I don't know why I wrote a p, 2s2, 2p6, 3s2, and then I'll have 3p6 instead of 5 because I have that extra electron. Now, a good way to kind of like double check your work here, the superscripts, so the 2s, the 6, the 2, and the 6, they should all add up to the number of electrons that given atom has. So let's start with the neutral chlorine atom. The neutral chlorine atom has 17 electrons. So 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 5 is 17. Good. Down here I have one extra electron, so that'd be 18. So we're on the right track here. Now, I do want to show you the shortcut method, but I want to finish the rest of this table first. So let's get to the orbital diagram. The orbital diagram is going to look like the little square method that we had before. All right. Now, if I go to nitrogen real quick, because that's going to be the example I'm going to look at, and I'm going to use a different color here. Let's use blue. Here's nitrogen. It's element number 7. Nitrogen has electrons in a 1s orbital, has electrons in a 2s orbital, and has electrons in the 2p orbital. So I'm going to represent these orbitals as squares. And on a test, if I were to ask you to write in the information for an orbital diagram, I typically give you the empty skeleton, so you'll get the empty boxes. So I know that nitrogen has a 1s orbital that I'm going to represent with this box. It has a 2s orbital that I'm going to represent with this box again. And then I have a 2p orbital set where I have 3 boxes, and they're all next to each other. I want to give myself a little bit more space here because I'm going to fill these boxes with electrons. So going back to your periodic table again, if I want to write down the electron configuration or the orbital diagram, I know I have 2 electrons are inside the 1s orbital. So it's 1s2, 2s2, 2p, 1, 2, 3. Now, with the orbital diagram, we really need to make sure that we're obeying Hund's rule, because I can fill in my electrons like this, and this would be incorrect. Because now I'm breaking multiple rules, actually. One, these two electrons have the same exact address. These two electrons have the same exact address. These two electrons have the same exact address. And then furthermore, I probably wanted to space these out so that each of them corresponds to one box because of Hund's rule. I want to maximize that spin, right? I want to maximize the placement of my electrons. So this would be incorrect. I'm still going to fill in my electrons from low energy to high energy. So it's going to be 1s2, 1 up, 1 down. 2s2, 1 up, 1 down. 2p3. And because I'm obeying Hund's rule, it's going to be 1, 2, 3. And this would be the correct diagram. So again, on a test, I probably would give you the skeleton of this, and you would, write that in. Let's finish this off. The orbital energy diagram. So the orbital energy diagram is going to have an energy axis. And the energy axis, 100% of the time, is going to be a y-axis. And that's the only axis we're going to draw in here. So I'm going to try and squeeze this like this. I'm going to draw an arrow like that. And I'm going to say that this arrow corresponds to energy, meaning the orbitals that are located down here are going to be lower in energy than the orbitals that are located up here. These are going to be higher in energy. And I want to represent the orbital energy diagram for a neutral nitrogen and then a nitride. This is going to be a nitrogen that has an extra electron. And so our skeleton, again, is going to have a 1s orbital, a 2s orbital, and you'll notice that I drew the 2s orbital higher than the 1s orbital because the principal quantum number, n, is greater than 1. So the 2s orbital will be higher in energy. But then the question you might ask is, well, what about the 2p orbital? Would the 2p orbital be drawn as the same energy as the 2s, or would it be drawn up here? It would actually be drawn up here, because if I have two atomic orbitals that have the same principal quantum number, but have different L values, meaning one is an S and one's a P, or one's an S and one's a D, one's a P and one's a D. The higher the L value, the higher the energy as well. That's something that we didn't tell you from the previous section, but that corresponds as well. So I'm going to draw those 3 empty boxes up at the top here. We're going to call this the 2p orbital set. Now I'm going to see if I can squeeze this a little bit higher, because I'm going to make this diagram is going to be the neutral nitrogen. So this is just nitrogen. The diagram to the right over here is going to correspond to the nitride. So it's still going to have the same boxes, 2s, 2p, but this is going to be a N- atom. So nitrogen, the neutral nitrogen, is going to have the same split up as the diagram that we have at the very, very top of the screen. There's going to be 2 electrons inside the 1s, 2 electrons in the 2s, and then 3 electrons spread out in the 2p. The same can be said, almost can be said for the nitride atom, except it's going to have 1 extra electron. So let's fill in the information that's exactly the same. The 1s and the 2s orbitals have 2 electrons each. It's when I get to the 2p orbital set that I have 1 extra electron. Instead of having 3 electrons, I have 4. So it's going to be 1, 2, 3, and then I'm going to squeeze in that 4th one in here. And that would be the correct energy diagram for that specific element. So what I want to do here, before I get into exceptions, because unfortunately, there's a series of elements on the periodic table that like to break the rules that we've learned up to this point. Fortunately for you, there's only 6 of them that you have to worry about, and they're all 6 of those elements that like to break the rules a little bit reside within 2 columns. So 3 of those elements reside in one column, and then the 3 other elements reside in another column. If I were to talk about other exceptions, If I go back to my periodic table here, these suckers, I'm going to highlight them with my laser pointer. These dudes, the lanthanides and the actinides, love to break the rules. They break the rules all the damn time. So on a test, I will never ask you to write down the electron configuration for any element that's located down here, because these elements literally have exception, like they have rules that have them as an exception, and then there's exceptions to those exceptions and exceptions to those exceptions. So really, for the electron configurations for these elements at the bottom of the periodic table, your best bet is to just memorize them. Fortunately, as students in undergrad, you will very likely not ever play with these elements, but if you end up working for a national lab doing uranium chemistry, like one of my really good friends who I went to grad school with, then you're going to have to worry about the electron configuration of those elements, but you ain't got to worry about it for this class. All right, so let's talk about our shortcut method. Let's insert a page here. We have about 20 minutes before this lecture has to conclude. We're making great time. Okay, let's scroll down here. Let's make sure I'm still recording too. I am still recording. We're good. All right, I want to choose a different element. Let's choose something that's a little bit heavier. Let's say I want to do selenium. So let's draw this in. All right, in red orange. I want to write down the electron configuration for this sucker. It is going to take absolutely forever for me to write this down. I am going to do it so that we have it as an example. All right. But just to give you an idea, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And remember, when I get to the d orbitals, these start at the number 3. 3d10, then we go back to the number 4 for the p orbitals. So this would be 4p, 1, 2, 3, 4. So that's going to be one hell of a doozy to write down. So just to clarify here, remember that the d orbital set starts at the number 3, 4, 5, 6. And when I get to the p orbital set, 5, 6, 7, the p orbitals still have the same principal quantum number motif as our s orbitals. It's the d orbitals that like to break the rule a little bit, and of course our f orbitals, which like to start at 4 instead of 5. Okay, or 6. So let's do selenium again. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Excuse me, I burped a little bit. 4p, 1, 2, 3, 4. Let's write that whole thing down. Selenium. 1s2, 2s2, 2p6, 3s2, 3p6. I have to look at my periodic table here. We're on 4, 4s2, 3d10, 4p, and I'll count this with you. 4p, 1, 2, 3, 4. So it's 4p4. Good Lord, that took forever. So you can imagine, for really heavy elements, you're going to be sitting down writing these things for a while, and that can be very, very annoying. Fortunately, there is a shortcut method. The shortcut method is called the noble gas configuration, which summarizes core electrons, we'll talk about core electrons later, as having the same electron configuration as a noble gas. That's what the noble gas configuration means. It's going to speed up the process a lot, because I'm going to take my electron configuration that I just wrote down for selenium, and I'm going to bundle up a whole bunch of these electrons with a symbol. So instead of having to write down 1s2, 2s2, 2p6, and so on, I'm just going to summarize and say all of them belong inside of one symbol. And the way we do that is we identify what was the previous noble gas to the element we are writing the electron configuration for. If I go to my periodic table, or your periodic table that you have on your wall, or you've printed out, or you have it on your screen somewhere, selenium is element number 34. The previous noble gas is argon. The noble gases are this column. It includes helium, neon, argon, krypton, xenon, radon, and Og is called oganesson, and it's an artificially made element. It's the heaviest element humanity has ever made. These are noble gases. The previous noble gas is argon. Argon's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. And because selenium has the same exact electrons inside of those orbitals, we're going to say that all of those electrons that are in the rows above it are inside of a symbol that we're going to assign argon. So if I go back to my example here, I'm going to write down the noble gas configuration for selenium. The noble gas configuration for selenium is the previous noble gas, which again is argon. We're going to put it in brackets. And then I'm going to finish the rest of the electron configuration for the electrons that are on the same row as selenium, which happens to be 4s2, 3d10, 4p6. Wow, that is way faster. So what I've done here, all the electrons that reside inside of this symbol are called core electrons. All of the electrons that are out here, these are called valence electrons. Now, we're going to go over this definition again in a little bit. I'm going to remind you again what the definition of core electrons and valence electrons are, okay? A core electron is the lowest energy state electron that does not create bonds. So these are electrons that just chill out. Core electrons, too low in energy, to make bonds. Valence electrons are high in energy. These electrons are responsible for any bond formation. So if I have two atoms and they create a bond between each other, whether it's a covalent bond or an ionic bond, the bond that is formed between those two atoms is done with only valence electrons, not with core electrons. Core electrons are already too low in energy. They are so lazy, so chilled out that you can't get them to do anything. The valence electrons are pent up though. They're trying to find a way to go to low energy state. So they're gonna make a bond. Now, or they can make bonds. A question you might ask at this point is, wait a second, Dr. Ochoa, why do electrons make bonds in the first place? I'm not going to give you the answer now. I'm going to tell you later why they make bonds, but it's something that you may want to think about before we get to that definition. There is a reason, and maybe based on our discussion here that we have, you may have already come up with a reason for that. You may already know why it is that electrons can make bonds. So to summarize, let's go back to our periodic table so I can show you the noble gas configuration for selenium. Instead of writing down that unbelievably long electron configuration, I just say, here's selenium. Argon is the previous noble gas. So I'm going to write down open parentheses or open bracket, argon, close bracket, argon, 4s2, 3d10, 4p4. And that's it. We're done. We don't have to worry about writing any more information than that. So that's how you write down our noble gas configurations. And a question I usually get at this point is, on a test, if you were to ask, if you ask me a question, Dr. Ochoa, Dr. O, would you want me to write down the electron configuration all the way, or would you like the noble gas configuration? And my answer to you is, I will tell you. The test question will say, please write down the electron configuration, and it might say noble gas configuration is allowed. Or it might even just say, write down the noble gas configuration. If a question says write down the electron configuration, and I only want the full configuration, then it might say, like, please only write down the entire configuration. If you try doing the noble gas, I'm going to mark off points. So read the question. The question will tell you whether I want it in one way or the other. All right. We have exceptions. There are some exceptions. Unfortunately, and this is strictly for our transition metals. These are there are only two columns that we have to worry about. And fortunately, those two columns are both columns that are in the transition metal block. They're both D block elements, all of them, all 6 of them. These elements like to break the rule. Specifically, they like to break, we would like to say, it looks like they break Hund's rule, or they break the off-bow principle. We're going to see in a second that they actually don't really break one of these, but there's a reason why these elements have an exception, or why they break the rules that we've described up to this point. So I'm going to go back to our periodic table, and I'm going to color the 2 columns. I'm going to circle them. The specific columns that like to break the exceptions are this column, which includes chromium, molybdenum, and tungsten, and then this column, which includes copper, silver, and gold. These 2 columns are exceptions to the rule. We'll see what I mean by that in a second. Let's choose chromium as our example. I want to write down the noble gas configuration of chromium. So if I go back to the periodic table, the previous noble gas to chromium is element number 24, is argon again. So it's argon, and then we're going to have some electrons that are inside of the 4s and 3d orbital. So what I'm going to do now, what I'm going to write down is what we expect chromium to be. So what we expect it to be. So that's going to be argon, 4s2, 3d, 1, 2, 3, 4. So let's write that down. That's what we expect. So chromium, Ar, 4s2, 3d, 4. This is incorrect. This is not the correct electron configuration for chromium. The correct electron configuration for chromium is actually, I'll erase this really quick, 4s1, 3d, 5, which looks kind of weird. That is kind of odd. It becomes very apparent why this is the case, why chromium actually is 4s1, 3d, 5 instead of 4s2, 3d, 4, when we write down the energy diagram for it. So real quick, here's my energy axes. I'm going to draw my d orbitals down here. There's 5 of them. There's 3dxy, 3dx squared minus y squared, you name it, all right? And I have a 4s orbital. Now, some of you might already see what's happening here, and some of you might be scratching your head thinking, wait a second. Dr. O, you drew the s orbital having a higher energy than the d orbital. Shouldn't it be the other way around? No, this is the correct way, because the principal quantum number for this s orbital is 4. The principal quantum number for this d orbital set is 3. 4 is greater than 3, which means this orbital is higher in energy than these orbitals are. So let's fill in our electrons the way we expect, what we expect for chromium to be, 4s2, 3d4. Now, before I continue, there are more atomic orbitals down here. The reason I didn't draw them is because I'm only interested in the valence electrons. Remember, these are valence electrons. All the electrons that reside in the core electrons don't do anything. We really don't care about them. So a question like this on the test might say, look at the orbital energy diagram that represents the noble gas configuration for chromium or some other transition metal. So we expect 4s2, 3d4, like that. That is wrong, because this downspin electron has a choice. Right now, it's sharing an apartment complex, or, you know, these two electrons have two different spin values, so they are in the same atomic orbital. They're not breaking any rules. But this electron is going to be kind of high energy. It doesn't want to room with this electron. It wishes it had its own atomic orbital. So what's going to happen here is this downspin electron is actually going to leave this orbital to go down here, because now it's in a lower energy state. Furthermore, the energy state that I placed it in, as soon as I put that downspin electron into this orbital set, you'll notice that the entire d orbital set is half filled. That is lower in energy than a non-half filled atomic orbital set. In fact, with a star here, I'm going to say half filled and fully filled atomic orbitals are lower in energy than non-half filled or non-fully filled atomic orbitals. So by placing this electron at the 3d orbital, the overall energy of everything just went down, and that's a good thing. It likes to be that way. So real quick, I have 2 minutes here. Let's do one more. Let's go back to our periodic table and choose a different transition metal. Let's do gold. Gold is a good one because it has f orbital electrons. So the previous noble gas is xenon. It's 6s2, but I'm not going to go straight into 5d here. Because from here, you'll notice that if you look at my atomic numbers, it goes 55, 56, 57, 72. Whoa, what's going on here? It goes from 57 down to 58 here. I have to fill all of these electrons. So my electron configuration is xenon, 6s2, 4f14, 5d, 9. That's what we would expect, though. This is an exception. So let's write down what we expect really quick. I have about 60 seconds here. It should be more than enough time. So gold is xenon. This is what we expect. Xenon 6s2, 4f14, 5d9. But it's going to be lower in energy for me to take this electron that's inside of this s orbital and put it inside of this d orbital instead. I can't put it inside the f orbitals because they're completely full. There's 14 inside of that electron set already. So this electron that's inside of the 6 orbital is like, I can't go here because that's already full, but I can go here. So that's what we're going to see. It's going to actually be 6x1, 5d, 10. I have 17 seconds. We finished just in time. So we're going to stop the lecture here. I am going to spend a few minutes talking about announcements here. In fact, the only announcement I have for you is again the Monday discussion. You're by the time you watch this, the discussion sheet is going to be posted for you, so you can upload it. Yeah, I know, phone. My phone is yelling at me. So you can download the discussion sheet on Canvas. I'm going to post the announcement to the lab Canvas site that you're assigned to. So if you are in the, let me pull up my calendar here really quick, because to this day I still don't know the section numbers too well. So if you are in the Monday section, your section number is 16814. In your Canvas lab site for section 16814, I will publish the discussion worksheet that has to be completed, and I would like you to have it finished by Wednesday. Now, the way you would turn it in is you would either email it to me, or you can just write your answer down on a piece of paper, and you can turn that in to me along with proof that you've completed the workshop, right? You would have to complete the entire thing. I did print out the workshop for everybody, so if you didn't grab it on Wednesday after I made an announcement about it last week, well, your only choice now is to either complete it online or print it out and do it like that. My last announcement is with regards to the lab. I'm not going to be teaching lab on Tuesday. That's going to be Dr. Miller. And the lab for this week is Lab 8, which is the emission of hydrogen spectrum. You're going to be playing around with lamps and stuff and diffraction gradients, so that you can see the spectral lines for hydrogen, neon, and a bunch of other lamps. There is no MSDS information for that lab. So if you're looking for the MSDS information, you're not going to find any because there isn't any for that lab. So you don't have to worry about writing that safety information. That being said, I'm recording this video on the 3rd of November. You're going to see this on the 6th. So I will see the rest of you on Wednesday in person where we go back to normal. And that's it. I'm going to stop this video now, and I wish you all the best.